Dear students, we are about to finish the probability part of this subject of this lecture. And the last topic from the theory of probability is central limit theorem. The central limit theorem is the theorem about convergence of sum of random variables. And before I start with this top of probability theory, we will study. I would like to tell you something about the convergence of random variables. So, you know probably the convergence of random numbers, of classical numbers, and then you calculate some limit of a sequence or limit of a function of a sequence of numbers, where the limit of this sequence is the number again. But in probability theory, we can consider both two types of convergence. First, the convergence of the numbers themselves, and then the convergence of the probability. So, when we speak about convergence of random variables, then we can consider either the convergence, let's say, almost surely, which means that the probability that the random numbers themselves converge is equal to 1. Yeah? So the first convergence is very similar to the convergence where we calculate the limit of the numbers themselves, and we only need the probability of such events causing that the limit of the random variable is equal to a concrete value is equal to 1. And the second type of convergence in this probability theory is the convergence of the probability. So the second convergence, which is called the convergence in probability, means that the limit of the probability of such events that goes closer and closer, whose image goes closer and closer to the image of some random variable, is equal to 1. So it means that the probability that the difference is larger than some given epsilon is equal to 0. And we say that the first type of convergence is stronger. So it means that if the random variable converge in almost surely, then it means that it must converge in probability as well. But the implication doesn't hold in the opposite sense. For our purpose, it is not so important, and you don't need to understand these terms deeply. The only thing I want from you is to be aware of the fact that there are more types of convergence in the probability theory. So I'll skip this topic, and I'll start with the central limit theorem, as I promised at the beginning. So the central limit theorem is about the distribution of sum of many random variables with the same distribution, where these random variables are independent. So we know that when we have xi independent identically distributed random variables. In the sequel, I will use only IID as independent, identically distributed random variables. Then, when we denote X, the sum of these random variables, then the expected value of X is equal to the expected value of the sum, which is equal to the sum of their expected values, and it is equal to n times the expected value of an arbitrary of these random variables. And because they are identically distributed, so it means that they have the same distribution, they have the same expected value, they have the same variance, they have the same everything. And so x2 has the same expected value as x1, x3 has the same expected value as x1, and so on and so on. All these random variables has the same expected value, which is equal to the expected value of the first one. Or we can denote it n mu, if it is more understable for you, where mu is equal to the expected value of x1, which is equal to the expected value of x2, and so on, which is equal to the expected value of xn. So if it is more understable for you, you can use n mu, and you don't have the index 1, which is connected to the first random variable, and it is maybe easier for you. What about the variance of x? The variance of x is equal to the variance of the sum of the random variables xi, which is equal to the sum of the variances, and it doesn't hold in general for all random variables, but only for the random variables which are independent. So this equality follows from the fact that they are independent. Otherwise, we would have to calculate with some covariances of these random variables, but because they are independent, the covariances are equal to 0, and then the variance of the sum is equal to the sum of variances. And it is again n times the variance of x1, x2, x15, it's up to you. So I will use variance of x1. Or again, if you don't like this index 1, you can write it as n times sigma square, where sigma square is equal to the variance of arbitrary of these random variables. So you can use this notation, but be aware of the fact that this mu and sigma square, which we used to use for the expected value and the variance of normally distributed random variable, is expected value and the variance of arbitrary random variable with arbitrary distribution. And so this mu and this sigma square is not used only for the random variables with normal distribution, but for this arbitrary distribution of the variables xi. Great. So we know that the expected value and the variance of this sum are equal to n times mu and n times sigma square respectively. What does it mean? It means that when we consider the random variable z, which is equal to x minus the expected value of x over the square root of the variance, using our notation, it is the sum of xi minus n times mu over the square root of n times sigma square. Then we know that the expected value of z is equal to 0 and the variance of z is equal to 1. And that's something what we solved 2 or 3 weeks ago when we were talking about the properties of the variance of a random variable. So this is not surprising. What is then the central limit theorem about? The central limit theorem is about such a random variable z where this n is large enough, because when this n is large enough, then not only the expected value of z is equal to 0 and the variance of z is equal to 1, but then z is very close to a random variable with standard normal distribution. And so the central limit theorem is about a special convergence of the sum of random variables to a random variable with the normal distribution, and using the normalizing procedure, subtract of expected value, and we divide it by the square root of variance, then we obtain the standard normal distribution of such a random variable. So why is it so useful? Imagine an example. So the central limit theorem says that z is standard normal distribution, or more precisely, when we denote it as Zn, then the central limit theorem says that Zn converges to Z with standard normal distribution. So, how can we use it? Imagine the situation that we threw a die. We started with the die 7 or 8 weeks ago, so we will finish with the die again. We threw a die 180 times. And the question is, what is the probability that there will be six spots on the die, which we usually use to call success. So what is the probability that there will be the success, there will occur the success at least 25 times, let's say. So standard solution is such that we consider a random variable which denotes some random number. So in our situation, it is the number of successes in written 180 trials. The random number describing the number of successes in a given number of trials has binomial distribution. Binomial distribution has two parameters. The first one is the number of trials. The second one is the probability of success in each trial. It is 1/6. So it means that the probability that the number of trials is equal to k is 180 choose k times 1/6 powered by k times 5/6 powered by 180 minus k for k equal to 0, 1, and so on till 180. And when we want to calculate the probability that the number of successes is at least 25, we calculate, in fact, the sum for k from 25 to 180 of these probabilities. So what does it mean? It is 180 choose 25 times 1/6 powered by 25 times 5/6 powered by 155 plus 180 choose 26 times 1/6 powered by 26 times 5/6 powered by 154 plus and so on and so on. In better case, we can calculate it as 1 minus the probability of complementary events. So it means that it is the sum for k from 0 to 24 probability that x is equal to k, but still it is 1 minus, and again, a crazy sum which starts quite reasonable, but at the end we have again 180 choose 24 times 1/6 powered by 24 times 5/6 powered by 156. So these numbers are very crazy, and it is much better than this number, because this number is calculated as 180 factorial over 24 factorial 156 factorial. In a better case, we can omit this 156 factorial, but 180 factorial, or at least 180 times 179 times, and so on, 24 members in the numerator will stay there, and it is really, really crazy to calculate. You need some software, you need to make some conditions for calculation of such a number. It's really terrible. And now, so this was the standard approach. Now, look what happened when we use the central limit theorem. We consider X, the number of successes, as the sum for I from 1 to 180 of xi, where xi describes the trial, the success or the failure in the ith trial. So it means that xi is equal to 1 if there are 6 spots on the die in the ith trial, and xy is equal to 0 if the number of spots on the die in the ith trial is less than 6. So it means, in fact, that xi has Bernoulli or alternative distribution with the parameter 1/6. Distribution of the random number describing the success or failure, 1 or 0. 1/6 is the probability of 1 of the success. It means that the expected value is 1/6. We will denote it as mu, and the variance is equal to 1/6 times 5/6, 5/36, and we will denote it as sigma square. Then, from central limit theorem, we know that the probability of such a sum, which is normalized by the description you can see on the slide or on the right part of the blackboard, we know that such a random variable converged to a random variable with standard normal distribution for n large enough. And in our case, n is equal to 180. It is really enough. Usually, it depends, of course, on the distribution of xi. But usually, when we have more than 30 random variables, we can consider that it is almost infinity. Yeah? So, in our case, 180 is n, which is really large enough. So we know that when we want to calculate the probability that the sum of such random variables is at least 25, we in fact calculate the probability that x with some normal distribution is greater or equal to 25, and we know how to work with the random variable with normal distribution. In the first step, we use normalizing. So, in our case, we normalize this sum so that we subtract n, which is 180, times mu, which is equal to 1/6, over the variance of x, which is n times the variance of xi, which is 5/36. And the same operation which was done on the left side must be done on the right side. So 25 minus 100 times 180 over 180 times 1/6 must be divided by 180 times 5/36. On the left side, we have the random number z, random variable z with approximately normal distribution with zero mean and the variance equal to 1. On the left side, we calculate 25 minus 30 is minus 5. In the numerator, we have square root of 180 times 5, which is 5 times 36 times 5/36, which is square root of 25, and the square root of 25 is equal to 5. So on the right side, the value is equal to -1. Okay, so it means that we transform this solution to the solution we know from last lectures. We want to calculate the probability that z with standard normal distribution is greater or equal to -1, which is 1 minus the probability that z is less than -1, and since z is continuous random variable, we can write the equality here, meaning that we obtain 1 minus the distribution function of standard normal distribution in the value -1. And we want to find this value, the value of the distribution function of standard normal distribution in the table. In the table, we usually have the positive variable, positive value for this distribution function. So we transform is using this relation to the solution that it is equal to the distribution function of standard normal distribution in the value 1. In the table, we can find the value 0.8413, and that's it. So without any software, without any calculators, without any technique, we can calculate only by hands and using the central limit theorem such a crazy example that in 180 trials in throwing a die, we will have at least 25 times the situation that there are 6 spots on the die. Yeah? So this is the meaning and the usage of central limit theorem. So I repeat that the central limit theorem says that when we take a sum of random variables with arbitrary distributions, the only condition is that these random variables must be independent and identically distributed. Then this sum behaves like a random variable with normal distribution. So it means that when we subtract the mean value of this sum, which is n times the mean value of each of these random variables, and we divide everything by the square root of the variance of this sum, which is n times the variance of the separate random variables, we obtain the random number, random variable, which converges to a random variable with standard normal distribution, and therefore we can calculate the probability of arbitrary situation using only the table for the distribution function of standard normal distribution. So that's it. Just a few words between we start the statistical part of this lecture. There are many central limit theorems in the probability theory. The central limit theorem can be considered in some special branches, also in some geometry, in many fields of probability theory. And in each branch, there are some special conditions for the inputs. And depending on who made the research of the central limit theorem, the central limit theorem has the special name. This central theorem, which you can see on the slide, is called Levy-Lindeberg central limit theorem. And the example which I showed to you led to the conclusion that, in fact, the random variable with binomial distribution converges for many trials, so it means for the parameter n large enough, to a random variable with normal distribution. And this special part, this special usage of central limit theorem is called Laplace central limit theorem. So in this case, where x has originally the binomial distribution, but we use the approximation of the random variable with binomial distribution by the random number with normal distribution, is called Laplace central limit theorem. Yeah? And in the literature, you can meet the central limit theorem connected to many other names of mathematicians. who studied the usage in some special branches. So there is not only one central limit theorem, but many central limit theorems. And the conclusion of all of them is that something converges to a random variable with normal distribution. So this is the main point of this theorem, the convergence to a random variable with standard normal distribution. So the central limit theorem is some kind of transfer from the probability theory to the statistics. Because the normal distribution is a very special usage in many methods and procedures of mathematical statistics. So I will start with some basic terms. First, I start with the aim of statistics, at least the aims we will consider in this course. The first aim is to make some theoretical model for the data from the practice. So what does it mean? It means that till now, we always know the situation completely. We know that we threw the die and the probability of 6 spots is 1/6. I give you the information that the number of clients in the bank is, I don't know, 3 per hour, and so on and so on. But in practice, you need to make these assumptions yourself. So in the practice, first you must observe the number of clients in the bank. In order, you can say that in average there are 3 clients per 1 hour. And to observe this, the situation and to set the model that the average number of clients is equal to 3, and the number of clients can be modeled by Poisson distribution because the clients come independently to each other, is the first aim, the first goal of the statistics. As I said, the model has usually some parameters, for example, 3 clients per hour in average in the bank, and these parameters must be also estimated. But of course, we want to have a concrete number, 3 clients per hour. That's nice. But we must be aware of the fact that everything in practice is random, and also our estimate is random in some sense. Because imagine that you observe the number of clients in the bank for 1 week. Then, from the data of this week, you can obtain that the average number of clients per hour is equal to 3. But when you observe the number of clients, for example, next week, you can observe that the average number of the clients is equal to 3.5. The week after, you can observe that the mean number of clients in the bank is equal to 2.7, and so on and so on. So in different weeks, you can get different parameters, and it means that each of the concrete value we obtain for the concrete week, we care about the interval in which the parameter, let's say, occurs where it appears. And so when we estimate the parameter, we estimate not only the concrete number, but also the interval around this number where the parameter can really be. And finally, we will test some hypotheses, meaning that we have some data. And for example, we observed that the number of clients in the bank is equal to 2.7 per hour. And we want to make some marketing strategy saying we have many clients in our bank. So we want to say that the average number of clients in our bank is equal to 3. But from our observation, we have only the estimate 2.7. 2.7 is quite close to 3. And maybe it can happen that another week we will observe the average number of clients to be equal to 3. So we want to test the hypothesis whether this number 2.7, which we obtained from our observation, is close enough to the number of 3, which would be nicer in our marketing strategy. So this is the third point, and we will start with the model of 1, 2, 3, with the model which we want to construct from the data. I'm sorry, there's some Czech word now in this sample, which should be a random sample, as you can see in at the end of the definition. So sorry, there's a translation mistake. I will correct it as soon as possible. So what is the random sample? A random sample, from mathematical point of view, is the random vector of IID, independent, identically distributed random variables, with some distribution depending on a parameter theta. And this is the random sample theoretically. In practice, we call also the collection of our concrete values to be the random sample. But in fact, what we have in practice is not a random sample. It is not a random vector. It is the vector of the concrete numbers. So it should be called realization of random sample. And so the random sample is the random vector. It means that when I give you some homework, go out to the street and observe the heights of 10 people, 10 randomly chosen people. Then the first of you will go out and observe the values: 180 centimeters, 175 centimeters, 160 centimeters, 2 meters, and so on. And the vector of 10 numbers. But another of you will go to the street and observe another 10 numbers: 160, 190, 195, and so on and so on. And so each of you will obtain the vector of 10 concrete values, but theoretically it is a random number, random vector. It is the vector of 10 random numbers at the beginning before you go out. So from the theoretical point of view, it is the random vector. What you obtain on the street is the realization of this random vector, the realization of this random sample. And then we will work with the following terms, following transformation of our random sample. First, we will consider the function which is given by this description: 1 over n times the sum of xi. It is called the sample mean, and you can see that it is very similar to the average. Because when you have, for example, the numbers 1, 3, and 5, 3 numbers, then 1 plus 3 plus 5 times 1 over 3 is equal to 3. It is the average. So this sample mean is really very close to the average, as you know. But again, you must imagine, you must consider these x1, x2 till xn to be random variables. So also the sample mean is the random variable. And you can see that in this form, we have the sum of independent, identically random variables. So it means that from central limit theorem you saw a few minutes ago, this sample mean should converge to a random variable with a normal distribution. And so here it is the first point, first part where we use the central limit theorem, which you saw here before, because the the sample mean converges for n large enough to a random variable with normal distribution. The second term we will work with is so-called sample variance, and the sample variance is very close to the theoretical variance. Look, we said that the sample mean is in fact something like the average, where we have a concrete n numbers, so not the random sample, but the realization of random sample, concrete n values. Then this xn will be a concrete value corresponding to the average. And as I was telling you from the beginning, expected value is something like theoretical average. And so this expected value is, in statistics, estimated by the realization of sample mean. And the variance of X, which was also very useful in probability theory, was calculated as the expected value of the square difference of X from its expected value. I said that it is close to the sample variance. And now imagine how we calculate the sample variance. Well, when we calculate the sample mean, we use 1 over n times the sum of xi, which means that we take all xi's in our random sample, and each of these xi has in fact the probability 1 over n that it will be chosen from the sample. And so when we have 10 numbers in our sample, the probability that I choose one of them, one concrete of them, is 1 over n. Yeah? So in discrete case, we calculated the expected value as xi times the or k times the probability that x is equal to k. Here we calculate it as xi times the probability of xi, which is equal to 1 over n. So the transformation or the term which calculates the expected value is in fact 1 over the number of observations. Great. So this is the first analogy, and now analogy of the rest. So we said that the analogy of theoretical expected value is the sample mean. It's here. Xi are random numbers. So these xi are these random numbers. Square of the difference is the square of the difference. So we need to include this expected value. And this expected value would be included as 1 over n. But what is the problem? The problem is that this sample mean and this average is in fact random is in fact connected with this xi. And when we have, for example, the values 1, 3, 3, and something, x1, x2, x3, x4, and we know that the average is equal to 3, then we know what is the last number. The last number is equal to 5. Otherwise, the average wouldn't be equal to 3. And so, in fact, the last number is not random in this sample when we know the average, when we know the mean value. So it means that when we calculate, when we estimate the variance of some random variable whose sample we observe, then we have only n minus 1 random numbers. Because the last number is in fact not random, it is connected to this average. It was just a heuristical explanation of the situation. Of course, we have to calculate it by standard mathematical methods that this is the best estimate of the variance. But for the basic explanation which we need, I think that this is enough. So once more, in the formula for sample variance, the expected value from theoretical variance is replaced by simple mean. The random variable x is replaced by the random variables from the sample. Square difference is square difference, and the expected value is calculated as 1 minus the number of random observations, and only n minus 1 numbers are random. The last one is connected to the sample mean. So this is the second transformation, which has very special usage in statistics. And as in theory, we worked with standard deviation, which was the square root of the variance. In the statistics, we will work with so-called standard, with so-called sample standard deviation, which is analogously the square root of the sample variance. So I'll skip this. Another term which is used in statistics is the term quantile, and the quantile is defined usually through the distribution function of a random variable, but maybe it is better for us to imagine the quantile on the graph of density. So imagine a random variable with the density of such a form, such a shape. Then the quantile is the number with some index. So for example, the quantile set with index 0.7, and this quantile with the index 0.7 is the number on the horizontal x such that the density the area below the density on the left side from this quantile is equal to 0.7. So in general, where we have the quantile z with the index beta, it means that it is such a number on the horizontal x which left the area equal to beta on the left side from this value. Yeah? So it is the border value which left beta, the probability, the amount of probability equal to beta on the left side from this value. Yeah? So in our purposes, we will use some basic quantiles. I will talk about it later, but the remark will be very important. So as I said, the normal distribution and central limit theorem working with the normal distribution is very special in the statistics. So imagine such a situation that the density is the density of a normal distribution with the mean value mu. And I said that when the variance is larger, then this curve is more flat. It is more sharp for smaller variances, and it is sometimes very useful for us to know what are the boundaries around mu, such that in the middle we have some amount of probability. So usually we care about 95%. In statistics, we use percents much more often than in probability theory. Yeah, so what are the boundaries such that in the middle between these two boundaries we have the area 0.95. And we can use the knowledge of quantiles. So if we know these quantiles, and we know that it is required to have the area 0.95 in the middle, it means that T's tail must have the area 0.025 and T's tail must have the area equal to 0.025 in order these two areas is equal to 0.05, and it means that outside these two areas, it means in the middle between these two boundaries we have the area 0.95. Okay, so when we know that this area is equal or should be equal to 0.025, it means that here we have the quantile with the index 0.025. On the other side, we have the quantile with the index, and now imagine what happens if the tail on the right side should have the area 0.025, then the area from this point to the left side should be equal to 0.975. In order, these two numbers together give us the error 1. So it means that the index of this quantile is 0.975. And that's the meaning of the remark on the bottom of this slide. When we care about the area below the density, which should be equal to 1 minus alpha. And of course, we talk about, I didn't tell you, but it is obvious that we care about the symmetric area around this mu. So when we want to make the boundaries of such a region where the probability that the random variable comes from this region is equal to 1 minus alpha, it means that the boundary points are the quantile with the index alpha half and the quantile with the index 1 minus alpha half. And so in our case, alpha was 0.05. The area in the middle, 0.95, was 1 minus alpha. And it means that alpha half should be left on the left side and alpha half should be on the right side. So it means that the index on the right, the index for the right quantile is equal to 1 minus alpha half. Okay? And it will be very, very often used in statistics. So, another basic term in statistics is the empirical distribution function and quartiles, median, and so on. So everything starts with the empirical distribution function. I recall that the distribution function cumulative distribution function is the function with the variable, let's say, u, is given by the probability that the random variable x is less or equal to u. Imagine that we have only the random sample. And consider a concrete realization of random sample, for example, 1, 2, 2, 3, 5. Then, in fact, we have a random variable taking 5 values, and one of these values is taken twice. So it means that we can take 4 different values, and the value 2 is taken with double probability. So when we care about the distribution function of the random variable describing which of these numbers is taken from the sample, then with probability 0, the value taken from the sample is less than 1, because it is impossible to choose a number less than 1. Then, with probability 1/5, we choose the number which is less or equal to 1. And the same probability holds for all numbers between 1 and 2. Then, what is the probability that we choose a number which is less or equal to 2? There are 3 possibilities from the total number of 5 possibilities that the randomly chosen number is less or equal to 2. So, the skip is 2/5 to the value 3/5. Then, the probability the randomly chosen number is less or equal to 3 is 4/5. And the probability that the chosen number is less or equal to 5 is equal to 1, because all the values we can choose from our sample are less or equal to 5. The same holds for all numbers greater than 5. Yeah? So in fact, this distribution function is calculated as, or is constructed as the distribution function of discrete number, discrete random variable, where all these values are taken with the same probability, 1/5. Yeah? In general, when we have n numbers in our sample, we calculate the probability that we randomly choose a number less or equal to a given number is the number of values which are less or equal to this number over n, or the number of all observations. And this is exactly what is described in the definition. Yeah? The distribution function constructed from a sample, which is called the empirical distribution, and the empirical meaning constructed from the data, is constructed so that for each real number, each real variable x, it is the number of values which are less or equal to x over the number of all observations. That's it, nothing else. Yeah? So it is the estimate of the distribution function from the data. And then we consider some quartiles. In fact, the quartiles are the numbers from the sample which which divide the sample to some parts or values. And so, for example, the second quartile, which is also called median, is the value which is in the middle of the ordered sample. And so when we ordered our observations from the smallest one to the largest one, then the median is the value in the middle. It is such a number which left half of the observation below, half above. So it means that in our case, this number 2 is the median, because 2 numbers are smaller, 2 numbers are larger. The first quartile is something similar, but it left only 1/4 of the sample below. So in our case, it would be this number 2, because 1 number is below, is smaller, and 3 numbers are larger. The third quartile is the same, but on the opposite side. So the third quartile means that about 3/4 of observations are below, are smaller, and 1/4 of the observations are larger. So in our case, it is the number 3 because 3 numbers are smaller, 1 number is larger. And so it is approximately the meaning of the quartiles, but they won't be so important in our lecture. And the most occurring element is called modus. We won't use it, so we can skip it. So imagine the example how to solve some basic construction of the model in statistics. We observe some duration till some breakdown of some instrument. It can be the observation to an arbitrary event, not important. In our case, we have these 21 durations. And so sometimes in, I don't know, in days probably. And when we construct the model, we first ordered the data from the smallest one to the largest one. And from this ordering, we can observe what is the smallest value, what is the largest value, and what is the median. And the median, which is probably only important quartile for our purposes, our median is equal to 1.4. And we can see that this median is much closer to the minimum than to the maximum. So it means that probably the values are concentrated more to the smaller values. So probably the model won't be a model of some symmetric distribution like binomial distribution or normal distribution, but probably we will use some distribution whose density is concentrated more to the smaller values. In fact, we observe durations. We observe time of waiting for some events which come independent to each other. So we suppose that the model will be the model of exponential distribution. And so we'll suppose that our observations are random variables coming from exponential distribution. So our assumption the data come from exponential distribution with the parameter lambda. And what does it mean? It means that when we denote x, the time of waiting for the next breakdown, where this is what I call the duration. Then, if x comes from exponential distribution with the parameter lambda, then we know that the expected value is equal to 1 over lambda. which means that lambda is 1 over the expected value. So it means that when we want to estimate lambda, we can estimate it as 1 over the average of the observed variables. It is not the sample mean because now I consider the concrete values, therefore I write the small x, but in fact it is the realization of the sample mean I was talking about. And this is only the estimate of lambda, so I will write this hat, which denotes the estimate. An estimate. So, in order to estimate this parameter, we need to calculate the sample mean from our data. So it means the realization of the sample mean, and the mean or the average of these observed values is equal to 2.471. What does it mean? It means that since the distribution function for random number with exponential distribution is 1 minus e powered by minus lambda x for positive x, and it is equal to 0 for x less or equal to 0. It means that when we draw this function with such an estimated lambda, it should be similar to the empirical distribution function, which is estimated from the data. This is the empirical distribution function. So it means distribution function estimated from our 21 observed values. And I'll skip this. On the right picture, now forget the left picture and look to the right picture. By the red line, we draw the distribution function of exponential distribution for lambda estimated as 1 minus the average. And we can see that really the points or really the functions are very similar. Of course, they won't be the same because we have only finite number of observations. So in our case, the empirical distribution function, or in our case, general empirical distribution function will always be pairwise constant. So there will be always these pairs. It cannot be the same as the distribution function of continuous random variable. But the question is whether it is similar enough or not. And in this case, we can see that it is quite similar. You need, of course, much more experience to decide whether it is similar or not. But believe me, it is very, very similar. There are much worse cases in statistics. And another tool, so this was the first tool to compare the empirical distribution function. Another tool is to compare so-called histograms. The histogram is the plot where we have the rectangles constructed so that on vertical x we have some interval with the same length. And so in our case, since the minimum of the observed values was 0.1 and the maximum was 7.8, I decided to take the interval from 0 to 8 and divide it to 8 intervals with the length 1. And the height of these rectangles is equal to the number of observations in the given interval. And so, for example, the first rectangle is the height of the first rectangle is 8, because we have eight values, 8 observed values in the interval from 0 to 1. The first 8 values caused that the height of the first rectangle is equal to 8. The height of the second rectangle, corresponding to the interval from 1 to 2, is 3, because we have 3 observations in the interval from 1 to 2. So you can see that the height of the second rectangle is equal to 3, and we continue further and further till the end of our data set. Great. And what does it mean? This histogram, in fact, means where we take the values more often and where the values doesn't occur so often. So this histogram is, in fact, the analogy of the density. The density describes where the probability is distributed more often and less often. So the same is the meaning of the histogram. The only difference is that the area of all these rectangles is not equal to 1. So it is arbitrary area. But when we draw this histogram in another scale, so that the area of these rectangles, of all these rectangles together, is equal to 1, then we should obtain something what is similar to the density. The density of exponential distribution is equal to lambda times e powered by minus lambda x for positive x and equal to 0 for x less or equal to 0. And so it is a function with decreasing exponent. And we can see that this function is quite similar to this histogram. When we draw both histogram and the theoretical distribution function, again with lambda estimated in this way, we can see that again they are very similar. The density goes approximately on the top of the rectangles. Okay, here is one rectangle which is quite above, but you can see that in the following interval from 5 to 6 there is no observation. So it is enough to have one observation instead of 4 times 8 to be 5.1, and it would be almost perfect. So really we can conclude from these pictures that this data comes from exponential distribution with approximately the parameter equal to 1 over 2.471, or what was the number? Yeah, so that is the way how to construct the model. And the last graphical tool, which is used in statistics, is so-called box plot. The box plot is the plot where we have a box somewhere in the middle, and the box has the lower boundary in the first quartile, the upper boundary in the third quartile, and in the middle of the box, not in the middle in the scale, but somewhere inside the box, we have a line corresponding to the median. Minimum and maximum are the boundaries of these legs of the plot. And the information which we obtain from this plot is how symmetrical the distribution of the values is. If it is symmetrical, then the box is somewhere in the middle, and also the median, the line inside, is in the middle of the box. Here we can see that the values are concentrated to the bottom of the plot. So we cannot talk about the symmetry of the data. Yeah? And we will continue next time with the methods of estimating the parameters. It was quite easier here when we have only one parameter which is connected to expected value, but there can be more difficult situations and we will talk about them next time. Thank you for attention.